Okay, let me say from the outset, this is kind of a point of privilege sort of thing, or a tangent that because we're online, you can totally ignore. You have my permission to turn this off if you have something more interesting to do right now. I just wanted to get in and talk a little bit about some of the stuff that in one of the kind of streams of my arc that got me excited about this intersection between the social and the technical. And I will admit that it is a piece that has not really been part of my research agenda in terms of what I've published, at least, but it continues to be kind of a motivating area for me. So I want to introduce you to some things that we otherwise you probably won't hit anywhere else in the program, and that may or may not be of interest to you. If you are interested in them, there are courses you can take at the university that might be able to take it a little bit in an interesting direction. So I started out in computer science, and at the time I was really interested in artificial intelligence, and there were a bunch of different kinds of ways of thinking about AI. The beginning of what we're doing now that's very popular for the current stream of AI, which is large language models, came out of a stream called neural networks. I was interested in that. The computing technology at the time really couldn't do neural networks justice. So some of it was theoretical. We didn't have like CNNs. We didn't have this ability to go back and do convolutional models that really worked, because you needed a lot more processing than you could really do to start. You had to hit a certain level of processing before they actually seemed like they were working in a real way. So, some of the ideas were already present even in the mid 1980s, I guess. But the practical application of it was very limited. And so it really kind of stalled. There was some sort of the things coming out of Lisp and a programming language called Prolog, these symbolic attempts to kind of do symbolic programming, where you gave it a list of ways the world worked and then hoped it worked out how they all linked together, kind of a networked form of programming. So that was one other way. But I was really interested in these sets of distributed computing models. And I was lucky enough as a grad student to go to a place called the Santa Fe Institute for a little bit, where they do some work on complexity studies. And so there's this intersection between large scale interactive models and so very, very simple computers, but lots and lots of them working together. In fact, one of the kind of the themes is this idea of the anthill, right? So the ants themselves may not be intelligent, but other kinds of hives as well seem to act as an organism on their own. And at the time, one of the people who worked in AI, Marvin Minsky, had these thoughts about kind of society of mind, that our minds were the same way, and that we had very simple processes that interacted, and that out of this emerged more intelligent behaviors and more intelligent activities. So that was a compelling interest of mine. Intersecting with this is this idea of social simulation. So, even if the players are not super simple, out of economics and other places, you were starting to get these questions of whether you could model markets and things like that by taking very simple actors, simple rational actors, which is kind of an assumption among a lot of economists. And can you, based on that, kind of see the emergence of this macro level set of markets? I've always been interested in the micro and the macro and how they interact. So I landed at Santa Fe Institute when a bunch of really interesting people were there doing work. And I want to kind of lead you through some of the pieces that I found really interesting about that. And so I'll start out with something that used to be a programming model that you had to, when you were starting out and learning how to program, if you were a first year computer science student, or if you were a hobbyist before that, you probably at some point implemented a computer program that simulated what was called Conway's game of life. And the game of life was a very simple cellular automata. And what that is a large collection of very small programs. It's not the way you usually programmed it, but that's the way you can think about it. So, for example, you would have a grid of little cells, and whether you as a cell turned on or turned off depended on what the cells around you did. So, if the rules were that if a certain number of them are on, then you turned on. If a certain number of them were off, you turned off. And there was a fairly simple a very simple program, basically, that allowed you to look at the 8 cells that were surrounding you on like a tic-tac-toe board, your very local neighborhood, and make decisions over. It's not really even a decision. Make a reaction over what was happening around you. At a very basic level, if you only have one of these sitting there, it's the stupidest program ever. But once you start to make these larger and larger, they start to exhibit behaviors that are interesting, right? Some of them might get to a steady point. Some of them may travel. You could design things that if you had an interesting starting point, it could like send things out and back. And some of these got quite large, and you could do actual programming using those cellular automata. My guess is that some of you may have read some recent science fiction that talks about this. The very popular science fiction trilogy over the last few years had people implement this actually within a virtual world. But people have implemented something similar in Minecraft as well. Basically, that's a little bit of what you do with with logic gates anyway. But in this case, the behavior itself was emergent. You didn't have to wire them up in any particular way. They would kind of do things on their own. And it turned out that this kind of behavior that was emergent from small cellular automata was duplicated in some ways in, for example, the ways in which certain chemical reactions happened, right? So it wasn't just this weird computing artifact, but it was something that seemed to be showing up in lots of different places, kind of consilient behavior that happened at different scales and in different sciences. And so understanding these kinds of systems became interesting. There's, at the same time, some thought around game theory. This is not theory about games, but whether you could treat behavior as a game with rules, I guess. And you've probably run across one of these basic rules, which was the prisoner's dilemma. And very briefly, the way the prisoner's dilemma works is if you've ever watched any police procedural, they get the two criminals, they put them in both in rooms where they're questioning them, and they say, well, it's either you or your accomplice. Whoever gives it up first gets to go free. But if you both give it up, then you're both going to go to jail. So in a singular prisoner's dilemma game, there's a very clear strategy, right? If you get a very small penalty for turning state's evidence, then you do it, because either you lose pretty big or you lose just a little. The chances that you're silent are very, very slim, because you could lose out more. So you have to do the weights so that makes sense. But generally speaking, what that means is that the choice for a singular prisoner's dilemma is that you rat out the other person. And that's why the police do it. It makes sense. A guy named Axelrod started to think about this in terms of other kinds of interactions, kind of negotiation, business negotiations, war and peace kinds of negotiations, international treaties, and that kind of thing. And so that kind of idea of the prisoner's dilemma does seem to show up in lots of other places. There's a little bit of a twist, which is it is an iterated prisoner's dilemma. That is to say, you don't just play it once. Does the strategy change if you play it over and over again? That's an interesting question. So you could kind of write a program that plays the prisoner's dilemma, and then there's lots of ways you could write that program. Think about it for a second, and you could probably come up with a little bit of a Python function that says, okay, how do I play this? How do I play this, right? But let's say that instead of having it, instead of doing that, what if we did this as a finite state machine? Now, I'll try to draw this because I don't think I can say it, and I have to do it in my head while I'm talking about it. But this idea of a finite state machine shows up in a bunch of different places. It shows up in cryptography. There's something called Markov models and hidden Markov models that do a kind of finite state machine, which is really important for early recognition of stuff, and actually does, again, feed into this development of LLMs, because in some ways, LLMs are a weighted finite state machine. So nerves are like this neural network kind of approach of a network of nodes that are weighted, are kind of an implementation of a kind of finite state machine. When I say finite state machine, what do I mean? I mean, it is a machine that has states, and that as you move to the next state, they're based on inputs from elsewhere, right? So you have certain inputs, and that changes the state of the machine. So one of the first implementations of a finite state machine, actually there had been some earlier than this, but was for a game that you could play tic-tac-toe using a finite state machine. And what that meant is you would, you had to, this is in some of the earliest AI programs, some of the earliest programs that were designed to demonstrate some kind of intelligence were done using, done on traditional games. And so one of the first of these was designed by Alan Turing, but there weren't any computers. He designed it before the computers could do it quickly enough, could process it quickly enough. And he wrote a chess playing program. Now you had to execute this on paper because the computers were too slow to do the process, right? But he'd actually written the program, and over time after his death, people had taken his chess program and coded it on a machine, and it worked great. But to start with, he had to do it on paper. Another one later on was an attempt to kind of show how you could build a program that played noughts and crosses, tic-tac-toe, using matchboxes. So what you would do is and this was the first machine learning model for gaming, one of the first machine learning models for gaming. And what it would do is you would have a couple hundred matchboxes that described the state of a tic-tac-toe game, and then would say what the next play was. And what you would do is if you went through this and you won, you would add something that would add weights to it that would make you play that move again in the future. I think someone has implemented this online, the matchbook version of this, but you don't want to really do it. Someday, if I have a lot of extra time, I will sit down and actually make all the matchbook. Do you guys know Matchbox? I'm saying matchbook, but I mean matchbox, little boxes that matches used to come in. It strikes me that I'm really old and not everybody has seen a matchbox. But someday I may sit down and replicate this in matchboxes. But for now, I'll point you to someone who's done this online if I can find it. I might have something written up about it as well. So what you could do that for that was done for tic-tac-toe. You could do that for this idea of the prisoner's dilemma, right? So you could build a machine that, given what the other person did, would then make a particular play, right? And the state would be, something that determined where you were at a particular time. So you might have just two states. You could have either defect, that is, rat out the person, or you could kind of try to collaborate, right? So you might have a box that's a defect and a box that's collaborate, and where you go from one state to the next is dependent on what the person played last time. So if you're playing this as an iterated game, you might be on, collaborate, and you might just sit here and stay on collaborate indefinitely until someone defects, and then you would go to defect. This strategy, which is when the person defects against you, you defect, you basically play what they played on the last turn, is called tit for tat. That's what we'd call it in English too. It's pretty straightforward. That is, as long as you don't rat me out, I won't rat you out. As soon as you rat me out, I'll rat you out. As soon as you then are nice to me, I'll be nice to you. Pretty straightforward, tit for tat. And Axelrod found that this was always the winning strategy for the prisoner's dilemma, for the iterated prisoner dilemma. And he talked about this. He applied it to his divorce. He applied it to nuclear treaty negotiation, and it ended up being kind of pretty influential on how people thought about doing negotiations, for better or worse. If you want to talk about the alignment between model and world, if the annihilation of the planet because we can't come up with good nuclear treaties are based on a model that is very, very simple, you have to worry about how those link up, and I'll get back to that in a second. I happened to be there in a time when someone named Melanie Mitchell was also there, and she was talking about evolutionary systems. And one of the neat things about a finite state machine like this is you can actually present it in a straight binary pattern. And this is really easy to do when I have a whiteboard, and I should have one of those pieces of glass that the people on YouTube have so I can write it out. But basically you can kind of represent the state of the machine as a binary, right? In this case, because it's you either rat the person out or you collaborate with them. So that's one of two states. So if you have, say, two states that are part of your finite state machine, and then you have the way they're wired together, you can talk about addresses. So if you have one in position 0 and one in position 1, and you have the labels for each of those, and then how you have them kind of wired together can also be depicted by these same kind of binary descriptions. So there's a way to kind of line this up so that you can say, what's the input, and then where do I go next from where I am? This can all be kind of represented in pure binary. And if you do that, you can come up with a random binary string of the same length, and it will actually describe a finite state machine. Now, some of these will not work, right? Some of these will just it's random. So how it negotiates those states is completely random. So theoretically, you could kind of run all the billions and billions of machines by just kind of going through and doing 0, 1, 0, and doing every iteration of possible machines. That would be kind of dumb. You'd have to wait till the heat death of the universe to actually get a result. But what Mitchell had figured out is what you could do for this and other kinds of finite state machines is you can take half of one machine and randomly cut it in half and connect it to the other half. And if you did this and you played the game over and over again and you had it simulate all of these in kind of tournaments, and then you took the winners and you had them have children by cutting their machines in half and linking them together, or adding a little mutation in there where maybe every once in a while a bit would get flipped. The next round, you would have machines that were maybe smarter, and maybe the winners of those could have babies, and winners of those could have babies, and winners of those could have babies. So anytime you can describe a mechanism using pure binary and then kind of do an evolutionary process, it is at least one way of searching through a problem space and coming up with a solution. I may link to, if I can find it again, there's a game version of this that makes a car that tries to get over jumps and things and learns over time how better to do that. There was an experiment with at MIT, I think it may have been Carnegie Mellon, where they did this with a locomotive, like a three-legged walking robot, and it did not seem like it should work, but they built the darn thing and it did. So you can come up with some interesting kinds of solutions by going this direction. At the time, they were also working on models, and I was interested in some models around kind of social classes, whether you could model these in a language that helps you think about having small actors interact in some way in a simulated set of rules. So it's not this restricted. You can actually have these have the behavior of each of these entities described in a way that is a little bit more complicated if you want. And then you can kind of run this in parallel and come up with a simulation of how this might result in some kind of structuration at a higher level. I was really excited about this as a process, and I think some people have done some interesting things with it. But where it breaks down is when you try to link that simulation with the real world. And this is kind of a perfect example of what we've been talking about all along, which is sometimes the models aren't close enough, you can't have the models tell you that the story is right. Even in Axelrod's work of the iterated prisoner's dilemma, I don't think that it is certainly has been highly influential, but I think in the end the problem is that the model is not representative enough of what real negotiations look like. And so it's nice to have if everything else is equal, this is a model that can tell us something. But if that model is just so basic and so bracketed off that you can't represent it in a true social context of any kind, then it falls down. So, I would love to think that we could come up with simulations, spaces that were fully simulating some kinds of limited social environments that were representative enough that those models did reflect in some way what was going on in the broader world. But so far, I haven't proven to myself that there is a model like that makes a lot of sense. So this is one of my things that I really wish it had happened, but it hasn't yet. Nonetheless, that thinking through of cellular automata more generally and questions of AI and evolutionary computing and kind of the broad questions of networks of thinking machines really kind of set me up, put me in a good position for when LLMs came along, because I'd already been thinking about this for a long time and what the social impact of machines that work like that are like. I think some of this is because I read a book when I was very young called Goethe, Escher, Bach, which is, I think, one of the more popular books. I'm sure most of you have read it. Many of you may have read it. If you haven't, I think it's actually a book that people either love or hate, or there are very few people that fall somewhere in between. But it was a thought-provoking. It's by a guy named Doug Hofstadter. It was a very thought-provoking book for me to read when I was quite young, and so that way of thinking about the way systems work has really informed not just my methodology, but also the way I think about social science as a whole. So there's my ad for a method that I don't use and I don't think is usable, and yet still has served me in interesting ways. And if any of you are interested in doing something in this area, again, there is a complex science kind of group at ASU, and they'd be happy to have you in their courses for an elective. And one of those is social simulation. And so since they are actually doing the work that I have put on the back burner, I might point you in their direction instead. But I wanted you to be aware of this existing as a thing and let you know that, at least for me, it's something that has really driven me intellectually for a long time.